Okay, so two tricky true-false questions about modeling, which is the process of going from real life to math land, and also about probability spaces, which are the main thing that is in probability class. You take the real life problem, you turn it into a probability space, and that's where you do all your work. First question, true or false? For a given, quote, real life situation and assumptions, there is more than one probability space that could correctly model it. And let's see what you guys said. We want to see what you said. Okay, so 48 people selected true. There is more than one probability space that could work. 15 people selected false. There is only one correct probability space. And the correct answer is true. So very good, very well done. I'm not going to hit reveal here because I don't want to reveal the next one. But sometimes there is more than one right answer, which is a fun thing about probability. There's always many different ways to think about the problem. You want to choose the one that is the most convenient. Let me give you a quick example of that and recap what we saw sort of last class. So, so this is a fact. And let's see if can I hide this. Yeah. There can be more than one probability space. Correct probability space. I guess before we do this fact, let me do another fact, which is there are incorrect ones. Fact. Not every answer is correct, so this is a good place to clear up some misunderstanding. Not every answer is correct. So last class we saw, as an example, we said if you flip two coins, and count the heads, the number of heads. So this is the problem we left off at the very end of the class on Wednesday. So if you flip two coins, you might think the outcomes are 0, 1, or 2, but 0, 1, 2 with the equally likely probability, equally likely, that's the one that just counts, that is incorrect. So this is wrong. This is incorrect. The correct answer is to do this one, heads, 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 tails, tails, heads, and tails, tails with the equally likely probability. The probability is equally likely rule. That one is correct. So this one is a big check mark. And the reason is there is a symmetry between sides of the coin. So the head side of the coin and the tail side of the coin, we know from our experiences in real life, those are symmetric and should be interchangeable. And you can change one coin in this probability space. You can flip the first coin from heads to tails by moving here, and that's why these things are all equally likely. In the 0, 1, and 2 probability space, there is no symmetry between flipping one heads and flipping two heads. There is no way to map flipping exactly one heads to flipping two heads. That is sort of fair. So that's why 0, 1, and 2 are not all equally likely, but heads, 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 tails, tails, heads, and tails, tails are all equally likely. So that is making sure you know that's not that every possible answer is correct. There really is. Sometimes there's wrong answers, but sometimes there's more than one right answer. And the example I'm going to show you is drawing cards. Drawing cards. So here I have a deck of 3 cards. A deck of 3 cards. What are they? I brought my big fun cards today. So we got the ace, the king, and the queen. So it's a deck of 3 cards, and I'm going to shuffle them and deal you 2 cards. So shuffle, 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 and I will deal out 2 cards. Let me put the 2 cards here. 1, 2. So deck of 3 cards, and we're going to deal out 2. So you get a hand of 2. And the question is, what could possibly happen here? Here is one way to do it. You can think of the 2 cards, and you can think of the order as being important. So there's the first card and the second card, and you could just think of what could happen in the first, what could happen in the second. So for the first choice, there's 3 things that can happen. The first choice. And those are either ace or king or queen. Let's make this king a little clearer. So the first card has 3 choices, ace or king or queen. And the second card, there's 2 choices for each possibility. So if an ace was dealt out in the first round, it could be either king or queen. If a king was dealt out in the first round, it could be either ace or queen. If a queen was dealt out in the first round, it could be either ace or king. And so finally, we have 6 possible things. 1, 2, 3, 4, 5, 6. And so the probability space is these 6 possibilities. There's ace-king, ace-queen, king-queen, or king-ace, or there is queen-ace, or queen-king. Those are the 6 possibilities. And again, by symmetry, knowing that cards are interchangeable, we think all the cards are sort of symmetric. The map that swaps 2 cards should leave things unchanged. All of these things must be equally likely. So this is a perfectly valid answer. The sample space is this, and the probability is the equally likely rule. And that is perfectly correct. So that is one possible answer. In this case, you can actually do a simpler way to do it. And that is to realize that in a hand of cards, the order actually doesn't matter. Getting dealt ace-king, so this event, getting dealt ace-king, is actually the same as that event over there, getting dealt king-ace. They are indistinguishable from the point of view of the hand you are given in a game of cards. So these 2 things are the same. Similarly, king-queen and queen-king are also the same. And ace-queen and queen-ace are also the same. So there's sort of this like duplication of effort. This is perfectly correct, but it sort of is doing twice as much work as it needs to do. So a simpler, also correct way to do it, here is an alternate correct solution. You could do or, equally good, you could have the sample space S, which is the unordered things. So you could do ace-king, king-queen, or ace-queen with probability equally likely. The equally likely rule we learned last time. All 3 of these things are equally likely. They all have chance 1/3. That is also perfectly correct. So in this one, they all have chance 1/6, but some of them are double represented, right? Like ace-king and king-ace. And in this one, they all have chance 1/3, but they only appear once. This is also perfectly correct. OK, so this is a sort of a classical example where when you are creating the probability space, there's more than one way to do it. If you compare notes with your neighbor, maybe it seems like they have the wrong answer and you have the right answer, but you could potentially both have the right answer. Notice if you calculate any probabilities, you should get the same exact final answer for the probability. So if someone says, what is the probability that I have an ace in my hand? Well, in this one, the answer would be 3 out of 6. No, that's a lie. 1, 2, 3, 4 out of 6, right? And in this one, the answer would be 2 out of 3. But 4 out of 6 and 2 out of 3 are the same number. So you get the same answers in both situations. OK, there's my example. By the way, I'll say this kind of thing is called a probability tree, and we're going to see a lot more of this in more and more complicated situations next week. So this is a very useful way to think about probability, and we're going to see exactly what it means to draw these branches and stuff like that. So this is a preview of a probability tree. Yes? We're going to get a remark about a probability tree.
Can we return to that coin example?
At the very top, yes.
Can you correct the probability space that was incorrect to make it a correct probability space?
Yes, this is a great point.
For example, if somebody communicated us the results of it in terms of how many heads we got, but they never told us what order of cards we got, how could I have a probability space?
Yes, this is a great. So this is a very good observation. So once you've done this example and you realize that 2 probability spaces, they can be equivalent, one way they can be equivalent is if one item in one probability space actually represents multiple items in the other one. So for example, this ace-king in this probability space with 3 items actually represents the 2 items, ace-king and king-ace. And in this situation, everything was doubled up. Ace-king and king-ace were twice, king-queen and queen-king was mapping down 2 to 1 down to king-queen, and queen-ace and ace-queen were mapping down to ace-queen. So this was sort of 2 to 1. But this idea can also work even if it's not perfectly fair. So we can fix the probability space from before. So the flip 2 coins. How many heads? How many heads? And one answer we saw already is this one: heads, 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 tails, tails, heads, and tails, tails. With all probability 1/4, all, let's say, probability of any event, any simple outcome, omega is 1/4. That is correct. But we can make another probability space that works. So here is another answer, another equally good answer. you could do 0, 1, and 2. Hey, wait a minute. I said 0, 1, and 2 is not correct. Well, 0, 1, and 2 with the equally likely rule is not correct. But the rule that does work is the probability of 0 is a quarter. The probability of 2 is a quarter. And the probability of the event 1 is not a quarter, but is a half. And this one is correct. So the equally likely rule does not work for 0, 1, and 2. They're not symmetric. But if you have these weirdo probabilities, a quarter, and a half, then it does work. Why does it work? Well, I've actually just grouped together things. So heads, tails, and tails, heads together, that became the event 1. Tails, tails became the event 0. And last but not least, I guess heads, heads became the event 2. So I've mapped multiple things. I've smooshed them down together. I've taken heads, tails, and tails, heads, and smooshed them together to make the event of 1 heads. And that's why the probability here is a half and not a quarter. It really came from 2 quarters put together. So this is a perfectly valid answer for this question, but it's not the equally likely rule. That's a good point. Yes, this is a more complicated example. Any other questions or comments? Are you satisfied?
No,
Okay.
I'm partly satisfied. So you flip 2 coins.
Yeah,
The assumption made is that there were fair coins.
that's right.
But if they weren't fair coins,
Yes. Then we have to
I
work
would
even
still
harder.
have those 4 outcomes. I could still have those 4
That's right,
outcomes. But could I apply the equally likely rule there?
That's true. So far we don't know how to do that. So far we know we only know how to do fair coins, because the only thing we've learned so far is the equally likely rule. And then when we start getting into probability trees and stuff, then we'll be able to calculate more complicated situations. So if the coins are unfair or something, we'll have to break it down by the first coin, second coin, and so on. And we'll have to use some rules, some multiplication rules to figure it out. But we don't know how to do that yet.
Okay.
Yes.
Yeah.
That's a great point. So far, there are only fair coins, and the reason it's fair is because we can only do the equally likely rule. That's the only rule we know so far, and so that has to be our starting point. Yeah, great point. Any other questions or comments about this example? Yeah. Yeah, the answer to the question, how many heads? Okay. Right. Yes. That's right. Okay. Great, let's go to the other true-false question. There were 2 tricky true-false questions in the warm-up problem. So the true-false, 2 people looking at the same real-life situation and assumptions could both do correct modeling and probability calculations. So both people are answering correct. They're not making any mistakes. But they get different final answers when they have different knowledge of the situation. And this one is also true. So most people figured this one out. So the correct answer is true and true, which most people got, which is excellent. I think this one is a little bit like weird to me in my brain. Like when you go to physics class, there is only one answer, right? Like there's some physics problem in the world, and the answer is 2 joules, right? There's only one answer. But in probability class, the answer depends on what you know or don't know. It depends on the information that you have. And I think this can be a really hard concept to get that is somewhat counterintuitive. So this is, I guess, the next fact on our thing is fact. Probabilities depend on information. Probabilities depend on information. So there's no objective truth. What is the probability? The probability is only in the context of what information you have. And I'm going to illustrate this. There's a really fun problem I like to do with cards that we're going to do next. That's going to try to illustrate this concept. And that's going to lead us into something called conditional probability. So let's see how that works. So here is the thing. So I'm going to have a deck not just of 3 cards, but now we're going up all the way to 10 cards. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I'm going to deal out a single card to somebody and give them a prize if they got the ace. So the ace is the winner. All the other cards are losers. The probability of winning, I hope you will agree, is 1 out of 10. But here is where the fun will begin. Let me make the deck, and then I will really do it. So we got the ace over here. Let's get the rest of the non-winning cards. So here's the ace of spades, the winning card. We got 2, 7, 8, 9, 10, 3, 4, 5, 6. Here are the other spades, 2 through 10. These are the losing cards. And now I will shuffle up the ace into here and deal them out. I do need a volunteer who would like to win a prize. And for prizes, my son school, they ran an event where I bought hundreds of dice. So I will give out these dice as prizes throughout the term. So who would like to volunteer to be the, all right, in the blue hat here, you must pick a card. And if you pick the ace of spades, you'll be the winner. If you pick a non-ace of spades, you'll be loser. Just pick the card. I will hold on to the card so there's no peeking or funny business. But just tell me which one you want to do. That one. OK, great. So this is the card that was picked. We'll put this card safely right here. And then if it's an ace, they're going to win. If it's not an ace, they're going to lose. But here's where the fun things happen, right? So the probability of them winning right now is 1 out of 10. And now we're asking, can probabilities change? Can probabilities change? And here's what I'm going to do. I'm going to reveal an undealt card from the deck. So here we go. Here a little. The 2 of spades has been revealed. Now the question, the card revealed is the 2. How does the probability of winning the prize change? Did the probability go up? Did the probability go down? Did the probability not change? That is your question to consider. I'll give you 1 minute to think about this. Did the probability change? And if so, by how much? OK, 10 seconds left. Make sure you get your guess in, what you think happened, and then we're going to discuss it and see how did the probability change. OK. Oh, the timer does not want to stop. OK. OK, let's see. What did you say? Reveal counts. OK. So this is, I think, the most tempting option. How could the probability change, right? Like in probability cost, you calculate the answer. How could the answer change? Well, the answer did change. And indeed, most people have figured it out here. The probability went up. So that is the correct answer. And I think this is the hardest part about this problem is just understanding that when you have new information, the probabilities can change. Probability depends on the information you have. When you get new information, you get new probabilities. Does anyone want to say why they thought it went up? That is the correct answer. Yeah. Yeah, that's right next. So before, one of the ways they could have lost is if the 2 was over here. If the 2 was the card that they chose, then they would lose. But that's impossible now, because the 2's here, and there was only 1 2 in the deck. So that's one way to think about it. We've eliminated one of the possible ways that we lose. And this is indeed the way to think about it. So I'm going to draw a little cartoon over here to sort of illustrate this idea. So this was the probability space before. Before, the probability space was the ace, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then after, right, it's the same thing. Let me see if I can do a sneaky copy paste over here. Can I? Oh, do a loopy. Before it is after. So before, they're all equally likely, ace through 10, and they all have chance probability 1/10. Let me write that down as well. Probability of any individual outcome is 1/10. What is the probability after? Well, you take all the possibilities from before. One of them has been eliminated, and that one is the 2. The 2 is no longer possible. So I call this cut away the impossible. Cut away the impossible. OK. That makes perfectly good sense. There were 10 possibilities before. There were 9 possibilities after. One of the cards has been eliminated. The thing that is a little bit tricky is what is the probability of each of them now? It's very tempting to think maybe that the probability of a 7, that didn't change. Like we never saw a 7. So shouldn't the probability of a 7 still be 1/10? And the answer is no, because the probability We just said it went up. So the probability of each of these things is no longer 1/9. It is it's no longer 1/10. Now it is 1/9. So the probability of any individual thing in the new space, I'm going to call this the new probabilities. They are 1/9. And that's because there were 9 cards, and sort of the equally likely thing still applies. So they were equally likely before, they will still be equally likely after. This 1/9, the fact that it went up from 1/10 to 1/9, and there's 9 things instead of 10 things, I call this renormalize. Renormalize. So basically, the governing rule is the total probabilities better sum up to 1. Here they sum up to 1 because there's 10 of them and they're each 1/10. Here, because we cut one of them away, they have to each be 1/9 so that they sum up to 1. So I call this renormalize. Normalize means sums up to 1. Renormalize means fix up what you had before, make sure it still sums up to 1. We're going to have more details on this in a second. Any questions or comments about this idea? So this is a really important idea called conditional probability, where you update the probabilities based on what you see. So the before-after in probability class, this is called a conditional probability update. Conditional probability. Okay. Questions or comments? Okay, we're going to go into more detail on how this works, but I do want to point out you can have all sorts of weird conditional probabilities. Like let's do some more fun with the cards. I'm going to take these top 3 cards, and I'm going to reveal them only to the front row, so you guys can see these. Okay. So now, if I ask them what is the probability, they will have a different answer than you, right? They have different answers. They have different information available. Maybe you take this card. You can look at that. Don't show anybody else. Now they have their own answer, right? So everybody looking at the same exact situation, what is this card, or is it going to be an ace or not, can have a different probability until it is revealed. And he's revealed the 4. Better luck next time. Okay, so what is the point of the story? The point of the story is probabilities can change depending on the information you have, and it can be different for different people. It can be all over the place. You can have any sort of weird story that reveals any weird combination of information, and that will change the probabilities. And conditional probability is how we keep track of this. So it's actually quite annoying to write this like, oh, we had probability before, probability after, call it P new. So there is a special notation that we use for this kind of thing. And that's what we're going to learn next. So the special notation for conditional probability. And this is an absolutely essential notation that is used everywhere, all the time. And it is a bit weird looking. Here's what it is. So we will write the probability of some event, A. Let me not use A, because A stands for ace already. Let's say some event, E for event. Instead of writing P new, we write it like this. We say given, and then here we put the information we observed. Information we observed. Okay, and this stands for, so this notation, this is like symbols, and what does it mean? It means the probability after the information is observed. Okay, so everybody can have their own information, and then you can calculate the probability of some event. You can calculate it many different ways using the information, and we use this really funny line notation. This line is read out loud as given. So we write the word given for this line, and we would read this as the probability of the event E given the information we observed, and that's some number. So as an example, the example that we just did, the probability that the ace is selected as the magical card, given that a 2 was revealed. I guess there's only one 2. Maybe I shouldn't say a 2. Say the 2. That is what happened, right? The 2 was revealed, and we calculated that. That was 1/9. So the probability that the ace was chosen after the 2 was cut away, and we renormalized, the probability was 1/9. And so that is an honest-to-goodness statement of math. This number is equal to 1/9. The thing we're going to do now is sort of derive the general formula for these conditional probabilities. So here is like a fact. We're going to find a formula for the probability of some event A given some event B it is written in terms of A's and B's. So this will be a formula in terms of A and B. Okay. Before I derive this little formula, and we'll see that it does give a ninth, any questions or comments about what these things mean? So this is I think this is the hardest part of probability classes, what conditional probabilities are. This is where things start to get harder. And this will appear sort of in every problem after today's class. There will always be some kind of line on the board like this. So it's an important one to sort of get your head around conceptually, as well as being able to calculate, which we'll be able to do in a second. Okay, let's derive the formula. And the formula has two parts. So cut away the impossible, right? So when B is observed, so for example, if B is the 2 was revealed, then everything that is not in B must be cut away. So in our situation, we revealed the 2 was not the card, so we cut that away. So the event we saw is that it could be ace 3, 4, 5, 6, 7, or 8, or 9, or 10. So this is the first observation, is that if B happens, so when someone says B happened, that's what we're talking about, then in order for A to happen, it must be both A and B. Okay. So we're trying to find the probability that A happens, but we already know that B has happened. Someone has told us we've observed that B has happened. For example, we saw that the 2 is the revealed. And if A is going to happen and B has happened, then it must be that both A and B have happened. And this is why A intersection B happens. Right? This is what intersection means. It means both events happened. And so the probability of A given B is going to be something involving the probability of A intersection B. It's going to be involving the probability of A intersection B because both things have to happen. In the case that was given before, the intersection is kind of boring. So the ace is the one where you win, and we know it's not the 2. So when you do the intersection of not 2 with ace, it's still ace. So in that example, the cut away the impossible, we cut away the 2, but if you're asking what's the chance you got the A, it seems like, okay, before you win if it's the A, now you still win if it's the A. So that one is not doing much, but nevertheless, in general, it is true. It's the probability of A intersection B. Okay. So that is the first part. That's the sort of the cut away the impossible. That's what the intersection does. It's cutting away all the things that were not in the event B. But next up, we have to renormalize. And when you renormalize, we say, take all the things that are left, that has to sum up to 1. So this is the cut away. The cut away. And next up, we must renormalize. Next up. Renormalize. Normalize what's left. So the entire probability after you cut away things must sum up to 100%. That's why it went from a tenth to 1/9, because it has to sum up to 100%. And the way to do this is to divide the entire thing by the probability of B. So this is the formula. So this is going to be divide by probability of B. And I think this makes intuitive sense if you think of it. We've cut away everything except for B. B is the only thing that is left. So the probability of B, even if it was only 1/10 before, now it has to get boosted up to be 100%. And the way you boost up a number to make it out of 1 is you divide by the number. So the probability of B is the thing you divide by. Let's do the example we did before. We'll do it with this formula. The example. So if A is the event, the ace was chosen. The ace was chosen. That has probability 1/10. Probability of A was 1/10. And B is the event. The chosen card is not the 2. The chosen card is not the 2. That was the thing that was revealed. So the probability of B is 9/10, right? So we are asking what's the probability the chosen card was the A. That's you would win the game. B is the event that the chosen card is not the 2. When the 2 is revealed, we know the chosen card is not the 2. And you can figure out that A intersection B is still the chosen card is the ace. So the ace was chosen. So that's probability of A intersection B is still 1/10. And so finally, we can combine these to find the probability. The probability of A given the information B, it is the probability of A intersection B divided by the probability of B, which is 1/10 divided by 9/10. And that is exactly our answer, 1/9. So the tenths cancel, 1/10 divided by 9/10, and that's another way to get to the same answer. Sometimes it's easier to do it the sort of intuitive way and puzzle it out, but a lot of times it's easier to use the formula, and the formula has a lot of power to it. You do some really hard problems by cranking through the formula if you know when to use it. Okay, that's the definition of conditional probability. The next thing we're gonna do, I'm gonna give you a mathematized question with 2 dice instead of cards, and I'm gonna ask you guys to calculate a conditional probability. But any questions or comments about the formula before we do that? Yeah?
Would we write B as 2 prime as the complement?
You could write that. I think it would be perfectly valid to say B equals 2. If you said what 2 means, and then you said it's 2 complements, that is a perfectly true statement. So A and B are just names for the event. You can name them anything you want. And it's true that in this case, B is the event. 2 is chosen complement. That's true. Yeah. So you can call them Tim and Bob, whatever you want. Yeah. All right. Any other questions? Okay, let's do a harder one where you're going to have to use the formula or figure out what's going on with dice instead of cards. And that's going to be in Mathematize. Dice game. Okay, so here we go. We have the two dice, and we're gonna roll the 2 dice, and you win the game if the sum of the dice is no more than 5. Okay, before anything is revealed, we know the probability of winning is blank. This is the kind of calculation we did on the first day. What's the chance if you roll 2 dice that it comes out to no more than 5? That's the kind of thing you can do. The new part in today's class is the updated probability, and that is we're gonna roll one of the dice, but not the other ones. So the first dice is rolled and revealed to be a. Let's roll it and see. So we shake the big dice, and we roll it. It is a 5. What is the chance that when we roll the dice and add them up, we get no more than 5? 0. In this case, it's quite easy. The chances, whatever they were before, they have gone down to 0. Because now it's impossible, right? It's impossible that the sum of 5 plus the other dice is going to be no more than 5. It's definitely going to be more than 5 because it's 5 plus something. So the chance went from whatever it is to 0. That's kind of boring. Let's do it again. So we're going to repeat the experiment. So same answer from before, but now we're going to reveal a different number on the dice. Reveal 6. Okay, it's 0 again. Let's do it one more time. 6 again. Oh my, I should go to the casino. Why am I in class today? 3. Okay, there we go. So the first dice is rolled and revealed to be a 3. What is the probability we win now? So the probability changes from this number to this number. We revealed it to be a 3. I want you guys to try to calculate it based on what you know, what we've talked about, and the formulas. And if you can do it, then you'll have a good handle on conditional probability. Let me start a timer for, say, 2 minutes to give it a shot. Okay, and as a reminder, we rolled a 3. Maybe I should write that on the chalkboard. We rolled a 3 on first dice. Okay, 5 more seconds. Okay. So we played the dice game. We rolled a 3 on the first dice. What is the chance we're going to win? Well, what was the chance we were going to win beforehand? What did people say for this one? And most people said 10 out of 36, which is the perfectly correct answer. I have drawn this on our probability space. So the probability space, like we've done for the last few classes, is this all the possible combinations of two numbers 1 to 6. And here, colored in green, this is the event that we win. So this is the win event. The win, let's call the event W for win. And the W is the event, the sum of dice is no more than 5. Sum is less than or equal to 5. That's the event we're talking about, and it has 10 things. So the probability of W equals 10 over 36. Very good. The interesting thing is to say what is going on when we roll a 3. So once you roll a 3, what's going on? And in this situation, people are quite split. Is it 6 over 36 or is it 12 over 36? Seems pretty evenly split. Let's do it on our probability space. So what is the event that the first I'd roll was a 3? That is, again, that is some event on this space. And in this case, it's this event. I will draw it in a big blue box. This one. So this is the probability. This is the event that we rolled a 3. What should I call this? I'll do T for 3. T for 3. So this is the event T is the first dice is a 3. First dice is a 3. And it has 6 things in it. So the probability of T is 6 out of 36, which is 1/6. So far, that's all good. The thing we want to do is we would like to do the probability. The question we need to answer is what is the probability of W given T? What's the probability of winning given that you rolled a 3? That's what we want. So again, there's 2 different ways you can do this. There's the sort of conceptual way. The conceptual way would be to say, okay, where do we win? Well, it has to be either a 3-1 or a 3-2. So this overlap over here, these two, that is T intersection W. We win and the thing we observed also happens. So the first dice is a 3 and we won the game. And there's sort of 2 ways that can happen, and there's 6 total ways. So the answer should be 2 out of 6. This is the sort of conceptual way to answer the question. Conceptual. Right? Everything is equally likely. Oh boy, when I scroll up and down, it moves. Okay, I guess I must not scroll up and down then, as a nightmare. Can I go like that? Okay. We'll leave it. So the conceptual way is 2 out of 6. What is the non-conceptual way is you use the formula. So you do the probability of W intersection T divided by the probability of T. And the probability of W intersection T, it is 2, but not out of 6, 2 out of 36. It's 2 out of 36. So the probability of that little red overlap right here, there's 2 of them out of the total 36, 2 out of 36. And then we divide it by the probability of T. We found that out. That was 1/6 already. So you divide them. So 2 out of 36 divided by 1 out of 6, which is also known as 2 out of 6. What's going on here? What did I do wrong? Oh, yes, okay. 1 out of 6 is also known as 6 out of 36. And so the answer is 2 out of 6. So you can either do it with the formula and get 2 out of 6, or you can do it sort of conceptually and get 2 out of 6. The correct answer is 2 out of 6. Okay, sorry, I got a little squeezed in there because the computer won't let me move the screen, which is a funny bug to have. Any questions or comments about this calculation? Let's see, how many people got it right in the end? Reveal a correct answer. Mathematize thinks all the answers are correct. Why does Mathematize not know the correct answer? Does anybody know? Yeah, that's right. It depends on the insert real life result. So if you do it with a 3, the correct answer is 2 out of 6, also known as 12 out of 36. That is the correct answer. So if you got 6 out of 36, you might have calculated the probability of the wrong thing. We want the conditional probability of winning the game given our new information. Okay, that is a great introduction to conditional probability. There's going to be lots more conditional probability. We have one more really important concept about conditional probability coming. Yes.
I want to go back to the conceptual
Yes.
one.
Yeah.
Okay, so given that you got a 3 already,
Yeah.
Why did we have to pay attention to all those other 30 points? Could we not just reduce our sample space and say, now I'm just looking at what I got on the second die?
Yeah, absolutely.
on the
So you
red
can think
die?
of there's a whole new probability space, which is just the second die, which it could be 1 or 2 or 3 or 4 or 5 or 6. And what you've done is you've essentially recreated this column of the big probability space. So the big probability space has both dice, but the column of it has one dice frozen at 3. And so this column is sort of the idea that you're saying.
And so
Yeah.
we know we would only get a sum less than or equal to 5 if I got a 1 or a 2 on that.
Yeah,
die.
exactly. A 1 or a 2. Yeah.
So we have just simplified our thinking, which is what
Yes.
people do all the time. They simplify their thinking, and they are still approaching the problem in the right way, but just in a very simple manner.
Yes, that's right. I think the real advantage of the complicated formula is when things get really hairy and you can no
Exactly.
longer imagine it, then it's useful.
Yeah.
So it's really good to be able to do both. When the problems are easy, the conceptual one is great. When the problems are hard, you need the formula. Yeah. Okay, let's do one last mathematized problem. And this is a really important thing that happens in probability. Sometimes you have two events, A and B, and a really interesting phenomenon happens, which is you're asking what is the probability that A happens? So what are the chances of you winning the game? And then you observe the knowledge of the event B. And something happens that is funny is sometimes the probability of A does not change. So whether or not B happens, the probability of A is exactly the same as it was before. So in the example we just did, the probability changed. It went from 10 out of 36 to 2 out of 6, which are not the same. But sometimes it doesn't change. So when is it unchanged? And we can write this statement mathematically. The probability of the event A is unchanged. That's an equal sign. Something is equal to something else. But what are the two things? You have to be able to read the symbols and interpret what it means. If you're able to do this, it means you're grasping the notation with the line. If you can answer this question, it means you understand you can read these things out loud in the right way. Okay, I'll give you 1 minute to puzzle this out. Read the options carefully. Okay, 30 seconds left to take your guess. Which of these means the probability of the event A is unchanged when you know that the probability or the event B has happened? Okay, time is up. Before I reveal the answer, let me say one thing I forgot to say on the previous problem, which is the homework that you have due next Friday will have similar problems. Roll 2 dice. You're given this thing. What's the probability of this other thing? So that's the type of problem you'll be doing on your next homework. So it's a good practice problem in class. Okay, let's see. What do you guys think? Which of these has this funny situation where the probability does not change? You guys are very sharp, 55 people, so the probability of A given B equals the probability of A, and that is exactly correct. This one is so important. This one has a very, very special word that goes, when this thing happens, we don't write this all stuff down. We just say the magical word. This is a magical word, just like all the other magical words we learned, that has to go in your probability vocabulary. Does anyone know what the magical word is? Yeah. Independent. We call this independent. Let's write down this independent thing, and then we will call it a day. Okay, Mr. Oh, I see this is a bug. Oh, I remember now. Okay, let's make a new page. Okay, we cannot escape this. It will be here forever. Okay. So the definition, A is independent of B. Independent of B. This means the probability of A is unchanged when you observe B. The probability of A is unchanged when you observe B. And in symbols, this is the probability of A given B equals the probability of A. So the probability of A given B is what it is after you observe B. The probability of A is what it was before. These two things are equal. The probability is unchanged. This is a super special word we're going to spend a lot of time on, but that is the definition. We will unpackage what this means next week. Okay, have a great weekend, and we'll see you guys on Monday.